Okay. Yeah, I think Ernest, Supaki, welcome. So welcome everyone. So we're just starting off, and we're just reviewing what we did last time, and maybe just to see what was the best score everyone got. And yeah, so I think we have 82 from Moses, 81 from Mercy. So we can just maybe have two or three people to share their screen. We just have a review. Ernest, Supaki, what was your score?
Mine was 81.
81. That's interesting. I'd like to see how you got that. So maybe you can have you share your screen. So today we'll also go into how to tune, or maybe what we've been trying this week was trying to tune the models manually. So we'll see how to tune the models in more, I'd say, automatic, or now using some algorithms within in machine learning to actually even make the tuning faster and get it perfect. So yeah. So who is ready? Artist, yours is ready.
Mine, I don't think I'll be able to share because see, I did it on another computer.
Okay.
But let me see if I can get it. I can get the
Okay.
yeah.
What did you change that resulted in a better score?
I changed the what? The random, I think the random figure, something like
Oh,
that.
yeah. Okay.
Yeah.
Okay.
I changed it to 98.
Okay. But maybe for everyone, I think we probably realize that with this one, despite like what we had mentioned was we mentioned that like you're supposed to get like, okay, maybe when you're working on a machine learning model, for you to deploy it, you want like a pretty, maybe probably like 95 something above 95% in accuracy in the predictions. 80% is not necessarily the best. So there are certain aspects you're going to see. So maybe as I think we have Moses preparing. So Moses, you'll just let me just go maybe through one of, or why we actually maybe getting a challenge, getting a better score. So everyone can see my screen. That's the thumbs up. It's okay. Yes, okay. Like so basically, oh, sorry. So basically, just to review, remember when we started the whole idea of machine learning, this is what I showed you the first time. And so in machine learning, we started with, we went to supervised learning, and we went to regression. So with the regression, there was linear, there was polynomial, there's logistic regression. So we've already had a look at that, and yeah, in a way, maybe sometimes you will get to the limit of maybe what regression can do, or the kind of question you're looking at. Regression is not applicable in it. So then sometimes, so you will have. We'll then go to classification, where classification is it goes basically classifying data into different groups. So we might have basically the same way you'd classify like oranges and bananas, and very many fruits, and separate them into their groups. So this is basically what we'll be trying to do in this one. But now this will be on structured data. We'll touch a bit on like an equivalent of classification, but now in unsupervised learning. In this case here, we'll not have the output labeled, so it will be more of us looking for sense in the data. So like you have no idea what the output is, but you just try to observe what's happening with the data. How can I'm seeing some clusters here and here. Probably there's a reason why. Maybe like for instance, with the example with the fruits, you will see that all oranges are, you don't know maybe the name of certain thing is an orange, but you told all of them are round, and for the bananas none of them is round. So you see, when you use the classification models, they'll classify all oranges separately and all bananas separately as well. So that's what we'll do here, and also we'll find some concept called dimensionality reduction. So you'll also see that's a problem we'll encounter in the data we're going to analyze. So yeah, so like I said, we'll go back a lot to this concept. So today we'll touch a lot here. We're even going to use several models instead of one. So before we just use one model, tune it and try to get the best results possible. But we couldn't get out of this box here because the score wasn't did not give us the confidence to maybe go into deployment. So yeah, and we are still going to use this for analyzing the accuracy of the model. So we'll still go back to this, basically on cross-validation and confusion matrix, a bit on maybe the others, but mainly confusion matrix and cross-validation. Yeah, so I hope you remember this as well. So this, when you're using functions, you would see all of these aspects, but they'll be calculated automatically and you get results immediately. So remember that.
Okay. Hello.
Yes.
I was really interested in the bit of how the different variables affect the outcome.
Yes.
Or which variables have more weight than the others.
Yes.
Someone
Yes.
is in the coastline. Is it somewhere? Because
yes.
We have the full course so that we can know what is coming up next. Because now I've seen like you've gone to unsupervised.
Supervised and unsupervised. So
Yes.
what you're asking about is falls under this dimensionality. So when you're checking on the different dimensions, so like maybe just as an example, like you might have data that has more than 10 or even 20 columns, right?
Yes.
So I think your question is on which one is the best column, or which one should I use, which one should I leave?
Yes.
So that's where this comes in. So what happens is like if you were to draw like a scatter plot, I think everyone, you've been exploring a lot of data visualization. If I give you a data with two columns, maybe it has an X and a Y, and there is so it will be very easy for you to draw. You could draw a scatter, a bar graph, anything, right?
Yes.
But then I can add a third dimension, and then I can add a third column there, and then you'll still probably figure out how to do it, maybe using a 3D plot. So you'll do an X, Y, and then add a Z there. And then there is also, if I add a fourth one, then probably maybe using Plotly, you might figure out how to do it. So if I add a fourth one, maybe you might do a scatter plot, do a 3D scatter plot, and then maybe make the size of the points to be big and other small. But then you see everything is starting to get complex, right? So if I add the fifth one, then you don't know what to do. And if I add the sixth one, it makes it even worse. So what happens is there's something called principal component analysis. We'll have a look at it here, and what we're going to do is each principal component analysis analyzes all the data points or all the different columns and sees maybe the weight with which they have to the final output. So you'll find some have more weight than others, and so you can actually exclude some columns because maybe they have very little significance in the final output. So you'll now be just focused maybe on 5 of them out of 10 or 20.
Okay,
So
that is coming in a later class, eh?
That we should do today and also in the next class. So we'll, opposite to now, as we explore more complex data, you're going to be doing, we'll be including that in your PCA as your in your machine learning model as you're choosing, or the steps to take here.
Okay.
Yeah. So that's. Any question? So okay. Okay, I think there is a malfunction here with the presentation, but basically, so what we've been doing is the graph in the front here. Just give me a minute. Moses, are you ready?
Yes, I'm still running the commands, but I'm not able to repeat 82, so I'm still getting 81.
Oh, okay.
Yeah, and let's keep trying, and then I'll let you know.
Okay, just share your screen and we go through that, and just share.
Okay.
I think the other person who got a better score was 81. I did get 83 at some point, and then I changed back, and yeah, still got, I think, around 81 as well. But just share your screen.
Can you see now?
Yes, I can. Okay. So maybe just take us through what mainly you are trying to tune, and what did you change?
I was trying to tune the test size and the random state.
Okay.
So you realize if you change, then the values below change as well. The accuracy. Yeah.
So maybe just to everyone, if we hold the test size constant, you realize that the accuracy doesn't change much, because you see, like the test size, like we mentioned before, was it's more like how much you're giving the students like if it's in a classroom scenario, it's how much you're telling the students what is in the exam. So the more you should try, maybe just try it, although also it depends on the size of the data. If you have a larger size of data, you probably can do more data for testing, but when the data is not so much, then we have a limit on maybe how much we can give it for testing. So if we hold it constant, more like at 0.3, you'll see that getting a score higher than 81 is a bit hard. So, okay. So maybe, yeah, so, and then also maybe the other thing you could do here as well is try integrate a for loop, so that when you're trying to analyze like the random states, create a for loop that now, instead of having all the different parts of this, all the cells in separate, have them in one cell, and also have them in one cell, like now what Moses is doing, and then create a variable that updates or plots. You create an XY that is plotting on a graph. So your graph will have X as maybe the random state, and then Y as the final score. So what happens with that is you'll now start getting a curve that starts from 0. You'll have a very bad score, and some it will flatline, showing that maybe going past a certain value, like for instance, maybe having a random state of 200 is pointless. Or it basically get the same score as having a random state of 30. So that's now maybe even what Moses is trying to do right now. So, okay, thank you, Moses. So maybe I can show you, there's a method we are going to use even today. So it's a bit complex, but it's now does what you are trying to do, but now explores all aspects of the model. So the other thing, did you try to tune the parameters on the machine learning model, like instead of the splitter? Is there anyone who tried to tune on the machine learning model, the hyperparameters there? Yeah, right, on cell 234. Cell 234, at the bottom there, where you have output of 234, you can see there are different values there, right?
Yes.
So did you try maybe, because all of this, like we mentioned, you can have a different value for each one of them. You can have a different value on each one of them, and it will change the characteristics of the machine learning model.
I didn't change from my side.
Okay, so maybe I can share, because what I was trying, I just held this the test splitting, the test size constant, and I changed the random state a bit, and then now it was more of playing around with the hyperparameters. But okay, so let me just share my screen. I'll show you the what. So you'll see, like, so the challenge we are having right now is on this concept. In machine learning models, especially now from the models we are going to use from now on, we are going to have these two challenges. There is a bias, and then there is variance. So the example I have here is of data that this is the blue spots, and if you are to draw a perfect, like not necessarily a perfect curve, but a curve that has a very the squared errors are very small, it will more like curve somewhere in between here, and with this you're going to get very little errors. If you are to use linear regression in trying to get the perfect line for this, you're going to draw a line somewhere here, like we have the red line here, but in real sense, you still have, you're not actually, you see this has a lot of errors, more than the curved line we have here. So this problem, if you use linear regression, there is something called bias, and bias is the inability of machine learning methods to capture the true relationship of what you're analyzing. And if you see what we were trying to do, no matter what we tried, how best we tried to tune the machine learning algorithm, we still got the same score. So probably when you get into such a scenario, that's where you'll find yourself looking for another model. And I think someone asked in the previous class, how do you choose, how do you know when to, or which model to choose? So there is also something we're going to see called pipeline. You can actually use several machine learning models, combine them, and once you combine them, have outputs from all of them, and see, even have the same pipeline giving you the best score from whichever model it will go to check. So So this is the problem of variance. And if the other challenge you get is if you can have bias or you can have variance, high variance or high bias. If you have high bias, you're going to end up with a line like this, and you see the perfect line is here, but it will have some errors, and so you'll end up underfitting your data. And if you give it new results, you're going to have a very, like, the error will be very high, and most of the time you'll end up not relying on that machine learning model. And then the other aspect of is called variance. Variance is now you end up giving, like, now if you reduce the maybe it's not maybe the best way of tuning an algorithm, but if it is to reduce the test scores to maybe 0.1 or even less, what you will have is a model that really knows how to, like, it's more of maybe what was happening before Matiangi. You'll now have students who look really bright, and you give them any exam and they score 100%, but in real sense is they were given the exam and they knew exactly what was there. So if you do this, then the problem is usually, and the same thing that happens with students, I think in Kenya, is the same students, you take them to university and give them now a different exam, and things are chaos. So when you have a model that has very high variance, it will fit perfectly with the test data. But when you give it new data, it's going to be very chaotic. It's going to have errors, a lot of errors. So this is what we try, as you're tuning your models, you try strike a balance between these two. You don't overfit and you don't underfit. Somewhere there, yeah. And maybe where the line lies between that is dependent on the industry you're in. So yeah, any questions on that? Anyone with a question on that? So don't forget these two. The variance and bias, you should always have a close eye on whether your machine learning models is overfitting. So make sure you always have a good percentage of the test data, so you actually see actual results, and maybe not necessarily by reducing the test data. So yeah, so maybe just go to the next section. So like I was mentioning, yes, someone has a question? Ernest? Ernest,
I was asking.
Yes.
Hello.
Yes.
Yeah, I was asking. At which point do you tell that the model is overfitting or underfitting, as in the score? Yeah.
Yeah. So maybe what I'd say, if when it's underfitting, you'll have even when you're with your test data, like what we are doing right now. As we are training, we are not getting, we're still having a big margin of error, and we're still getting a big margin of error even with the test data. And what will happen is, with now new data, it will even be scoring probably worse than it's scoring right now. And then with overfitting, what will happen is, you see, like, you'll get a model that scores 98. And then when you give it new data, immediately it will even score as bad as a 50. So that's where you'll know that maybe there's something wrong with the model and it's not able to handle new data. And like we mentioned last time, is if you're making a model right now, you have your, like, ideal data, that not necessarily ideal, but you have your data that you're testing and training the model in, but eventually you want to deploy the model to actual use, and when it's there, you don't want it to have errors. You want it to replicate the same percentage score, like the accuracy score that it was showing when it was being modeled. So if the score is going low, you probably overfitted it. If it's still errors or the score is not good even when you're training, probably you're underfitting and maybe you need to change your model. Yes. Yes, Steve, you have a question?
Does including too many columns, I mean
Yes.
too many variables, cause overfitting?
Probably what will happen with that is you might end up with underfitting or with a lot of bias where you will find the model you have is unable to even make sense out of what is happening. So most likely that's what you'll see.
Oh, and in relation to that, what do we do to the variables which have very high correlation? Do we like remove one and remain with one, or we just put them all?
So the other thing we'll see here is like I mentioned in various corridors of machine learning, you will find some concept called the Cast of Dimensionality, and it's what Steve was asking about. So it's possible to have several things, like for instance, like when you're predicting the weather, if it's very cloudy and it's a specific maybe type of cloud and the humidity is high, then you see like having high humidity and the temperatures maybe going too low, they all have a very high correlation maybe to rain coming. So yeah, it's possible to have several columns that are highly correlated. But now, when you now go into dimensionality reduction, that's when we're now going to say, or this number of columns are the ones giving us the most impact on the final output. So we should probably concentrate more on using this in our machine learning model and ignore some. Yeah.
Okay.
Yeah. So the next section we're going to go in, I'll cut across, this will be classification. And basically what we'll do in classification, we're going to see data. It will be under supervised learning where you already know this is maybe an apple, or there's some data set we'll use like for even the previous ones we were using, they can work perfectly with classification, where you already know the output. So for instance, I've already told if the data, all oranges are usually a certain color and they have this shape, they are round and the diameter is this size. So when you're looking at those aspects, then if you have those characteristics, then it's very easy for machine learning model to know an orange and maybe an apple. So for instance, in this picture we have here, I think these are what are they called? The big ones here. I think maybe the pumpkin family, but you see the diameter here is bigger, and then they probably look similar to oranges, but the diameter is bigger, the color is different. You might have also oranges, but maybe same oranges, but they're different species. So round, but this one is almost yellow, and this one is almost maybe orange. It's different for lemons as well. Maybe the diameter is lower. So if so, then the different data sets you're going to see is, and then the interesting thing here, even I think Steve, you'll come back to your point. You're now going to see we have more than 2 columns. So you'll have diameter, we have maybe color, we have maybe shape as well, or all the columns might have a figure that is showing a certain relationship. It could be maybe if there's even one I was checking on obesity, like you'll check height, you'll check weight, you'll check age, you'll check all of those things, and all of those things. Now the models you're going to look at today, they make sense out of all of those, out of all of these aspects. One easy way of doing it is like, or maybe just a simple way of visualizing what's happening. Sometimes if you just throw a 3D scatter plot, you'll see some points starting to cluster together. So these models here, you'll see them, that's what they start doing. they more like look for relationships between points that are close. Like for instance, k nearest neighbors, that's what it does. It will see that there's a certain cluster out there. You'll get one point and checks the relationship between the next neighbors and clusters them together. So that all of that. So that's basically what you're going to see. Mercy has a question. Can fixing for multicollinearity make the score go high? Maybe I think it can, because probably I think because you'll remove some aspects that are not don't have maybe it will affect it a bit, but also it will save you computing power. So instead of analyzing aspects like within the data that don't have are not really like it's more of computing power you're using, but they don't really have much impact on the final score. So you will save a lot on computing power and maybe just finish analyzing much faster. Yeah. So yeah. So like a good example of this we use in industry is we analyze the quality of how well glass is cleaned, and we actually use a machine that uses image processing. So it will be able to inspect a glass tell that it's not well cleaned, and it will go back to cleaning, and another one will be will go now back into filling. So this, it's more of and it's something that it's a model that does it so fast, like almost I'd say like maybe 4 bottles, 10 bottles every second, and it does it very accurately. So yeah. So that's one maybe example you'll see in use outside now the learning environment. Any question? So in classification, we'll go through a few of the models. So one of the basic ones we're going to see is called decision tree. And then they will look at k nearest neighbor, support vector machines, naive Bayes. There are a lot of them, but once maybe you get the idea of what these ones are doing, all the others will make sense. And what you'll see is these ones, they just have a different approach, but they're just trying a different approach, but to get the same result. But also you'll find that the scoring for these ones, all of them are different. So for instance, in the, like, I think one of the exercise we can do today is maybe since the data we were analyzing looks like there's some bias, it's unable to score better or get a better result. Maybe we can try some new machine learning models. This classification, maybe logistic regression wasn't the best to deal with that, and see if we can just get a better score from that. Any question? The other thing I think you can mention is it's possible to not get a good score because of the size of the data you have. If you have very little data, you might be training your algorithm, but it's still not unable to do better. So even maybe in real world, you'll see we don't analyze maybe very few data points, like maybe 5,000. It's more of several million rows of data. So, and that's what you're going to use to actually do your predictions. So, yeah. So, unless there's any other question, we can go into decision, please. Okay, I think I was supposed to show how I did mine. So let me just show something. So this. So this is what we are going through. So I did a bit, we're going to look at this concept, I think maybe like once we go through the different machine learning algorithms, what Moses was trying to do, you are trying to tune this, or maybe on the different test size and the different random states. So what is this like machine learning model called grid search? If you grid search is it's more of it's just a it's an algorithm that helps you to go through every single possibility within a machine learning model. So maybe grid search. So if you go to sklearn grid search, you're going to see this. This is the syntax for it. So the syntax for the grid search is you'll just call the library and then you'll just tell it what estimator you're using, and then there's the param grid. Param grid is now all the hyperparameters within a specific machine learning model. So for instance, in our model here, we had called it ML grid, right? Okay, but so there's what we were looking at in the. Okay, I think I need to run all of them. I'll skip this. And this.
Just a question, Steve. Is it better we work from Kaggle, or is better we use this application, Anaconda?
I think they basically do the same thing. You remember the other one I showed you called Google Colab?
Okay.
They basically do the same thing. The advantage maybe you'll have now when you're using the likes of Colab and Kaggle is you're using an external computing power. So for instance, when you start doing this grid search and we just decide to go all out, it will be much faster using it external, like the Kaggle. And even the steps we are doing, you'll see that they're basically the same. So there is no problem. You can just use either. The only advantage is maybe in computing power. That's the main one that I see, and maybe sharing information. But you can do whichever is convenient for you. The other two need internet always on when you're using them. So yeah. So whichever you'll find convenient, you can use either of them.
And that's also the option of you can run all commands instead
Yes.
of running one by one. With Kaggle.
Oh, okay. Maybe there's that option as well. But the reason maybe we do, or like I go for this is, Jupyter is more like a learning platform. It's very easy. Like you see, if you do a machine learning algorithm, or if you do programming and you write the whole code, like you can use VS Code here, and it's usually just chaotic if you are learning. But if you're maybe like, see, for this one, will not give you a chance to. Maybe you just have to write the whole code, the whole code, and then run it. But with Jupyter, it gives you the convenience of writing one line, test it, and even see what's happening with it, and then go to the next step. So that's basically the advantage of using this.
Okay.
That's okay. So anyway, so like so basically what is here is So with grid search, what I was just doing here is, so this is the syntax here. So like we mentioned with this, you give it, you tell it the estimator you're trying to use, and then give it a grid, param grid. So param grid, you can give it all the aspects within the specific estimator you're using. So like this is now for logistic regression. I specified the n jobs. This is maybe the parallel jobs that are being done. So like you see this, the more computing power you have in your machine, the better. So you can have this as many as possible and it will do the job much faster. And then there's also the number of iterations. This, if you limit this to very few, then it will only maybe like the iterations are the number of times it's going to try to get the good score. So if you limit, the more you limit this, the less it's going to test, and probably you'll not get a better score. But the other thing you'll see is this will take a lot more time. So you're going to test so many aspects. It's going to take a lot of processing time, take a lot of time. And then there's all of this, like you remember this is what we were trying to tune. Like for me, I saw going past 30, I wasn't getting any better score. So I just stuck to a random state of being somewhere. I was just testing between 1 and 30. And then there's this, basically you can try, if you check the hyperparameters within any model, you can just try and see all possible scenarios. So with grid search, it's more like, if you're familiar with the concept called brute force, it's trying every possible scenario. So it will try maybe like, so for instance, maybe for random state, where random state is 1, it's going to try all possibilities where the maybe class width is 1, 2, 3, all the way up to 30. Combine with this one, all of those, all possible combinations, and trying to see what the score is. When the score is not better, it tries the next one, until when it will get the best score, and then finally give you an output. Or maybe it runs out of iterations. So with this, what happens is you'll do that, and you'll do that. It will give you all the board. It will, like now what's happening here, you'll see it stepwise what it's doing. And when it gets an error, it will show you. When it gets a better score, it will show you all of that, and then finally you're going to get your score. So like I had said, I was interested to see how someone got 83. But the combination, because now with grid search, you're looking at every possible combination, and despite doing that, I still got 81. So yeah, so basically that's how I went through this. We're going to learn how to use this grid search. It's not the best, so it's just, this is like I said, it's brute force. It's just because you have the computational power, just decide to go through every possible scenario. It's going to take more time, but you'll get the score. You'll get the perfect combination of this. Okay. Any question? We're going to go through it with the other models we are going to check on. So maybe you don't have to type it in right now.
The solver is what?
The solve. Sorry. Let me just share my screen. Which one?
It's something. There's the class weight, and there's the solver.
Okay, you're seeing my screen?
Yes.
Okay.
On the parameter grid, you have the number of jobs, maximum iteration.
This one here.
Yes.
So, okay, so like I mentioned, each machine learning algorithm has different hyperparameters. if you come to the documentation here, you'll always find, so here you'll find the default state. If you use the machine learning algorithm without changing the states, changing anything, it's going to use these defaults. So like all of this. So like you're asking about the solver. If you come here, you're going to see what they mean. So for instance, for the solver, it's an algorithm. So this, so you can see like probably SAG and Saga, you can go deeper into this documentation. You'll see the actual math on what's happening with that, like they're here, or you'll see the lanes here. But basically, these are just different techniques that the machine learning model is using. Sometimes it's different depending on, it's going to tune a certain aspect within the algorithm, but it's also dependent on the type of data you're looking at. So maybe going all out for all the possible combination is not the best. So you have to maybe check on what kind of data do you have. Like you see, these ones are best for small data sets, like this SAG and Saga. And then for multi-class, that's when you're now going to go for the other two. So yeah, but and every single model you'll see these aspects are different. So just go through each one of them and yeah, try change the values. So yeah, so here you can, when I give it this way, I'm telling it to check all steps, maybe from 1 to 30, and it can be as crazy as you want. It will take, the only thing is it will take longer. It will take longer, but eventually you'll get an answer of the best combination it found. The other interesting thing with this one is you can even do now a grid search of multiple algorithms. I think they have an example, one example here. So I think they usually have some examples. I think, yeah. Okay, so this is logistic. So you'll find, so you can choose different machine learning algorithms, give different combinations, and it's going to go through all of them, and eventually it will give you a better score. So yeah, because it will literally go through everything that is there. So yeah, but that's just one. So there are different methods of doing the optimization. So like the ones we look at today are these ones here. So there's grid search, there's random search, there's Bayesian optimization. So you can imagine, like in a Kaggle competition, whoever is able to choose the best model and combine this, the best combination of this, or the one that even maybe works the fastest, because you will find maybe also they are checking on computational power. So then how fast you're able to get the result back. Then you might find maybe, yes, you're getting a 96 like the top guy, but his is working much faster than yours. So you need to see how best to choose this. There's a concept that's come up, I think from 2018 to some 2018 called automated machine learning. So with automated machine learning, they now combine all of this, and they combine models. You'll basically just give it the data, and then it will do everything else for you. So yeah, it's more of just learn and see how to combine all of this, and you're able to get the best results. Any question? Everyone okay? Yes. Yes, Steve, do you have a question?
No.
Okay. So now the next thing we're going to look at is something we call decision trees. maybe for more from a philosophical point of view, if you look at the world, I kind of see it this way as well. From the time, if we are Christian, from the time God created the world, it's more like decision trees that were working from them. You give Adam the choice, and it's maybe what human beings we have. We always have choice. For anything, it's always a choice of two. Most of the time, it's a yes or a no, or it's this or this. So this is a concept that you will not only see it in machine learning, and even in machine learning techniques. This is a very old concept. It goes back into 1970s. That's when they were started using it. But if you look at nature, it's always two things. Lion chasing an antelope, you decide to stop or run, and yeah. If you decide, for instance, if there's a lion chasing you, if you're an antelope, run, you won't be eaten, or you don't run and you definitely eat them. So basically, what decision trees tries to do is it's more like the bottom side of a tree. So you like, if you're looking at the roots, or you just turn the tree upside down, and you're going the way the branches go out. So you'll always choose. You'll always choose between two. So with decision trees, the algorithm just analyzes the data, so it will start from the bottom. So for instance, the data set we were analyzing in the previous class, it will start with the result and start checking all the data that was this was a diabetes data set. Everyone who had diabetes everyone maybe from one of the different columns we have. So everyone who had diabetes had maybe their blood pressure at this point, or everyone who had this had, so it will go back all the way to the first point. And then depending on the number of columns, it will create several trees. So as it's creating the trees, then it creates the trees and creates all possible combinations that are there. So, and then when it's now testing, it will be more of just taking the data as it is. So when you give it data, like now a row that has the 3 columns, it's just going to check the first thing. So for instance, like one column is the shape round. Yes. Is the shape more than 10 centimeters? Yes. So if it's more than 10 centimeters, this is not an orange, or maybe it's a gourd or something like that. And then if the path is different, it will go all the way until we get this. So if we go to for the syntax for writing this is simple as this. So you'll import a library called sklearn tree decision tree classifier. So with this, you'll just give it that, and then and remember back to this. So this is just the same part we're going through again. So for the next examples, actually, like maybe what we can do, since we had already split on done the splitting on the previous graph, or on the previous data, we can try use a decision tree and see what the score will be. So maybe just I think now we go into coding. So I think we can start a new one. Or okay, so first is we can just try on the one we were using. So what will happen is, so you can just maybe if you want to just make sure everything is correct. Decision trees. Scalar. Oh, not sharing my screen. Okay, so we can just start off with just go to the sklearn library, and then you'll find the syntax on how to do a decision tree. So this is it, and these are the different hyperparameters, how to use them. So what you'll need is this one here. So if you go to the previous data set you were checking on, just import this. And then you'll also need the machine learning model. So so you can call it anything. For this, you could just not give any values, and if you actually call it here, you'll see maybe you'll see the different hyperparameters it already has. Okay. Yeah. So the next thing, like we said, the steps will always be the same here. So it's more of just this. And then maybe we can also try so predictions, and then as you're copying this, make sure you have the correct name for each one of them. Decision tree, and then maybe we can have this on its elements on. So like I mentioned, fitting is usually just straightforward. For the this data, it's not very big, but once you do that, then you just do the classification and test with that. And yeah, probably it's not working so good, but yeah, so you can already see, like the other one we got an 80. I think even just straight out of the box we got a better score. So you can see this one gets 71, but we haven't done any tuning. So yeah, that's the score. If you go back to, you can go to the, there's this, if you go back to this here, our drive folder, I think everyone has a link. You go to the folder, you can go to, you'll find all the material we are going to use here today. So just go to this here, go to classification. Some of the data we're going to use is within. Okay. So this is some of the data we are going to use. The chi-forces. Also for the guys in banking, will be a lucky day today. So we'll also use. Okay. So basically, just go to this folder and download these two. This is the data we're going to use today. Thumbs up if you've navigated to that point, please. Has everyone understood how we've just gone through this? So it's yeah, like I mentioned, it's usually a bit underwhelming because it's very straightforward. When the moment you just fit, it's more straight to this. Yes. Has everyone managed? I'm also sending the link to the chat. So just check on the chat for the link.
Have you sent the link?
Just a minute, I'm sending it.
Okay.
But it's the same folder we've been using. So just go back to this. Yeah, so it's same folder, so just go to it, you'll find the data there. There is also a few examples of maybe how you can do it, and also an exercise. But today we'll use the kyphosis data. So yeah. Has everyone managed to get it?
Which file exactly? Which folder?
So under classification, there is decision trees. There's this folder called decision trees. So you'll have these two files here, kyphosis and loan data. Kyphosis and loan data. That's okay.
I'm downloading.
Okay. Okay. So there is the default. Is the default. So once you create your file, also make sure you're in the right folder. So once you download the data, make sure in the right folder, and then in the folder with those, then we can start off. Then import pandas, or we just try import all the libraries we are going to use. Though, like I said, you can import even the machine learning ones here as well, but sometimes it's, since we, maybe for the sake of learning, let's just import them when we are going to be using them. Okay. Has everyone managed to download everything? Definitely. Okay. Okay, I'm not sure I'll be using Matplotlib, but yeah. Okay, so we import the kyphosis data. Then we'll go immediately into exploring it. So DF, can just have a look at what's happening with it. So I think this is usually, it's data on the kyphosis data. It's a data set that's been shared, I think, even on Kaggle, you'll find it there. It's a competition that was there, I think, like 2 or 3 years ago. So it's a data set of people who were found to be, they had what is it called? I think it's spinal cancer. But basically, that's the data and what the characteristics that were in those people. They already, funny thing you'll see is there's a lot of outlier data, like there's someone who was 158, but maybe it's on a different planet, so maybe there was someone who was 158. So maybe let's just see what's happening with the data. And yeah. The guys who are very quiet, are you following? Mary, Purity, everything okay?
Yes, yes, I'm following.
Okay. Well, okay. If you have if there is a problem or if you want us to maybe explain something, just make sure you give us a heads up. So anyway, so like you've seen from this data, we can go on a pair plot and then we can color it based on this here, where it was found to be absent or present. So we can give it a hue of that specific kyphosis. Okay, it's just the same name. So maybe let's just start with this and say something I left. So every time when you're doing, like we mentioned last time, every time you maybe get an error, always go to the bottom side. It will try direct you, and then and then the debugger will direct you where the problem is, and then also within the other lines you're seeing here is the library that it's using. And as it's trying to put in the data that or the aspects you've given it here, they'll maybe you'll see where the function is unable to handle that. So yeah, so You can just use that to quickly be able to see what's happening. So with this, you can already see the general distribution of the data. Also, this kind of like can help you to see the relationship in terms of if there's any correlation or not. Yeah, and also you'll be able to see some outliers in the data. So like for instance, like age, like I mentioned, maybe it's on a planet where
a bit on the hue. What hue did you use?
I used this column here, the kyphosis column. Just check on the spelling, it's a capital K. Okay.
And what's the difference between that and what you had done before? Because you had used palette before.
Yes.
And I see the graphs are different.
I think maybe let's just check on like we've always done before. Just goes to Seaborn. So this is a pair plot. If try always use document. You'll never go wrong if you use the documentation. Sometimes you'll overthink on something that you actually that's very more like that's something that's straightforward. So with the palette is more of the kind of color you're going to use. So you'll see like maybe like the one I selected at first, it will come maybe probably red and a blue. And then you can choose, maybe it might be a report and that you're doing at work and you want to customize even the colors to be your company colors as well. So you can use this and maybe go deeper into the documentation. You will find the different palettes that are there, and they are different, but you can also use a default. And when you use it on default, you'll use this palette. Where is it? Yeah, so when you use it on default, it uses none, but yeah, so it just comes with this normal, I think it's orange and blue. Okay, so that, but this, I think maybe when you're doing in the previous section, in the previous cohort, or this previous section you are in, you are doing data exploration and cleaning, and so like you'll have dealt with these outliers, like you could remove them. But like I said, for purpose of learning, maybe here we're going to assume the data cleaning is done and you just go straight into data analysis. If you check here, maybe you can start seeing like there's a cluster of those who are present and who are where it's present and where it's absent. You can see there's a cluster here and there's one that's here, depending when you check the number and the statistics. When you check the age and the statistics, maybe not much, but yeah. But anyway, we'll just go into now the machine learning models, and those will help us see better, or they'll analyze what's happening. So you already know what the logic behind the machine learning model. So the next thing we'll do is just, you can do more data exploration and maybe even clean it a bit more, but yeah. So let's just go straight into this train test. So this is the library we use for splitting the data. You remember the X and the Y? A capital X, it's in the syntax of that. So here, like I think last time we selected the specific columns, but you can also just choose to drop the one column you're observing. the one column that was the target. Sometimes, like I think in the previous data set we were looking at, it was the last column. For this one, it's the first column. Yes. So you split the data, so you now have the X and the Y. It's always an error, so just, yeah, there's a P missing. So the faster you're able to debug, life will get easy. Otherwise, you might find yourself giving up a lot or too soon. So test Y train, or you could go back to the section we were looking at before and just copy paste this as well. It's the same thing we are doing.
Steve, what did you do?
Yes.
Your command seems to run, but mine gave an error. Data frame object is not callable. Or there was something called drop.
Oh yeah, I dropped that column. Huh? So this one will drop this specific column. It's working. If there's anyone with a challenge, just share your screen. Just tell me to close mine, and then we'll check on what the problem is. Then this was also in the syntax. Just you choose the test size. So this one, let's work with 0.3 as well, and maybe no random state. That's no random state. So then next,
I'm still getting an error.
Okay, just share your screen. Let's have a look. Please share your screen.
Okay.
There's a H missing after the P. Just scroll down, and you'll see. It will direct you. But yeah, so okay, for me, when I get a syntax, or maybe when you get an when a cell doesn't run, or when you get a fault, you should kind of be happy, because yeah, it makes things easy and fast. It's like a learning moment for you, because next time it will be very easy for you to figure out or spot where the error is. So it's always good. Yeah. By I think also programming kind of starts making you to be more keen. So you'll notice, I think it's gotten a bit better with Python. I still code in C++, and a simple thing as this will make your whole code not run. And it's even worse when you did a big project. You've done a big project and it has several files, and there's a semicolon missing. The whole code will not work. And you can spend a whole night looking for that, depending on which platform you're on. But yeah, I've had that trouble. I think Sparky can share that as well. I think probably gone through that. So yeah, so next thing we'll do is just now we go into the machine learning. We call now the decision trees, since we want to use decision trees. So sklearn dot tree import. So this you can use in the previous section. We were doing regression. You can there is a decision tree regressor as well. So when you're doing a regression problem as well, you can try look at that. So next thing is we create our model. So decision tree model. So you can call it anything really. So this just it holds. It's the one that holds the classifier we are going to use. Okay, so after you do this, like we've done in the previous section, just call the model and dot fit. Then give it the data for training, X train, and Y train. So yeah. Next thing we're going to do is make the predictions. So once we've done the fitting, you now try tests on new data. X test. Oh, there's a syntax error somewhere. Can anyone spot it? Okay, so can anyone spot the error? Because it's something we've done that's not okay. We imported this. Anyone anyone who spotted the error? I can't see it. It's basically incorrect. Oh, yes. Thanks, Mercy. Sometimes it's thanks, Mercy. I think I was okay. It's the same as what we were doing in the previous one. So yeah, there's something I forgot to add that. Yeah. Should we take a break? Everyone okay? So yeah, so basically you just do your predictions, and then you remember there was the graph, the library we were using for getting the reports. So you'll get the confusion matrix, and you just get a complete report that's showing us everything. So that's the next thing you do. And the interesting thing is, for all machine learning models, we'll actually just be doing this. So I'll show you maybe for purpose of this, we're just going to combine all the cells. Then we just print the classification report, give it Y test. With predictions. So this one we get a 68%. So the other thing I think I want us to do is, since we're now going to just follow the same steps for all the machine learning models, let's just combine all these cells. Anyone with a problem? So for all the machine learning, all the models we're going to check on are like this. So that's basically, and then the other thing you're going to see is, like, every time you run it, probably will get a different score. Does anyone know why that's happening?
What's an 80?
Yeah, so yeah, and even just running it, again, see 76. Does anyone know why that's happening? Anyone? I guess.
Maybe it's because it tries grouping the data over and over and over again.
Yes, and then also, even within decision tree classifier, there is a random state. So you can get a different, different result for different, for the same data that you're analyzing. The other thing you'll see is, in the next class, we'll do something called a random forest. A random forest is basically now taking this decision tree, since this is just one tree, and it combines the different trees the same way we are seeing a different result for every tree. So every time we run this, we see a different tree. It's a different tree that has a different score. So it will probably be wise to just do several trees, combine them, and then maybe get the average, or get the best score from the combined trees. So that's basically what random forest will do. But yeah, so like this one, it will be different. So maybe right now I got an 80, 76. Someone else has an 80. Maybe we can also just check on the hyperparameters for decision tree, and we try input different, we try tweak it a bit and see if we'll get us score. Before we even maybe go into using grid search, let's try just do it manual and see if you can get a better score. So when you go to decision tree classifiers, and the classification, there is this one here. All of these are aspects you can change. You'll see this. There's a lot of theory into these two, using Gini or entropy criterion. Maybe won't go into all of them, but the best way is also, like I said, try visualize what's happening in the model. If you can draw a graph and change maybe change the different aspects and progressively see what's happening with the graph, you'll have a better understanding of this other than just reading through them. Okay. Any question? Any question? So that's basically just a general overview of decision trees and how they work. So we'll also look at there's another aspect where, like you remember, I mentioned something called explainable AI. So the other challenge you will find yourself in is you'll make a model that works. And then tomorrow you'll be asked, we don't understand what you're doing, and it works, but for some reason we don't know, maybe you're cheating. So yeah, so you need to be able to explain your machine learning algorithm, and that's why I'm saying the graphs will help a lot in trying to explain what is happening, and also maybe whoever might be asking might be very he's very honest. He's just trying to understand how your machine learning model is and probably see if it has any weaknesses. So I don't know, there's a website that called Explainable AI. I'll try get it. I can't locate it right now, so I'll share it as soon as I get it, but it will help you understand and be able to explain your machine learning models to your co-workers, and also maybe as you're doing pitching, maybe the whole project, you'll be able to explain what's happening instead of maybe calling it a black box that gives you the correct answers always. So that. So the next, so any question? Any question? So that was decision trees. Yeah, if you look at nature or you just look at anything, most of the human aspects or even in nature, that's basically what happens. It's always two decisions until you get the final result. Or even where you are right now, it was based on a decision tree that your brain followed. Yeah, and probably. So the next thing we look at is k nearest neighbors. K nearest neighbors is this is it works in okay. It's more of I'd say it will look at you'll give it, like you see from the syntax here, you define the neighbors that are there. So once you define the neighbors that are there, then it will analyze and more like cluster the different. When you have a scatter plot, it's now going to more like check everything that's near a specific one. It will take a random spot, a random spot, or maybe a random plot, and then it will now check all the characteristics of the points that are around it, and then now create clusters that are around a specific one. So the same way the other one was checking on maybe like if checking the different aspects of the columns and eventually clustering them together. This one you'll specify the number of classes that you're looking at. So the good thing with, since this one is supervised, we are going to just assume we already know the number of classes that are there. So for instance, in the data set we are looking at, we have 2 that is, it's either present or not. So we'll just specify 2 neighbors. So there's one here and another one there. And then, but like when you're dealing with unsupervised learning, sometimes you don't know what's happening with the data, so you'll just start at 2 and test the whole data set, see what's happening, if maybe check on the accuracy of it, and yeah, until you get now your final and until you get the most accurate one or what's working best in that. When you plot all of this data out as well, and maybe add the hue for, in unsupervised learning, you add the hue for now the clusters you found, you're going to actually see the different classes that are there and now eventually be able to name them. So that then the next one we look at is, so we're going to go back to coding, but I think let's just look at the next 2, and once we look at the next 2, then we'll go back to coding because it will be just one line. So there's another one as well that we call support vector machines. So this picture right here next to this here is it shows a line. So the same way we were working with the maybe like with regression, this will now find like the borderline between the different spots or the different points within the scatter plot. But what happens is it creates this border here where it's there's this margin and then there's this soft margin. So this machine algorithm will not only run once, but it runs several times and starts analyzing the points between or that fall within the soft margins. And from that, it will check maybe the error and how they are classified, and it will slowly optimize the same way we were looking at, I think, gradient descent in linear regression. So it will slowly optimize until it gets the perfect point where you have the best score from that algorithm. So that's basic. And from the syntax, so the library we'll use is called is still from Scalan svm.svc. And then these are the various aspects for the hyperparameters for the machine learning algorithm. So there's that as well. Then for naive Bayes theorem, this is a very interesting one. So very much the same as the way the decision tree was working. So this works, and you'll see it being used a lot even in the current situation we are in. It's a probabilistic model where it checks the probability of maybe, or the chance of maybe something based, maybe probably like following like a tree, the same way the decision tree was following, but now it will make the next decision based on the probability of the first decision it was checking on. So for naive Bayes, so this is basically the formula it's going to use, but an example, a good example of how it's being used right now is if you check maybe like what they're doing with the truck drivers on the roads with corona. If you are tested and you are found negative, then there is a very low probability you have coronavirus. So even in the next border, if you show the results, or now the decision that already made was you are not infected, then the probability is much lower. So that's an actual example of how they're using Bayes theorem in society, and it's used a lot for almost everywhere based on those aspects. But now, maybe for that example, it's only one-dimensional. There are sometimes, for instance, in our case here, where now you'll find if, like the example I'd given, if you have an orange that is, if you have something that's class, for instance, we are looking at the fruits. If something is round, then it's the probability of it being a banana is very low, because maybe the aspects of a banana are different, and there is no way we are going to go that way. So the good advantage with this, it's work way much faster. The computational power compared to the other models, this one will do it much better and will be much faster. So we'll just analyze and see from the various how it's going to analyze. We'll see if it is going to do better with default results, or even maybe if we tune it a bit, if it will give us a better results. But also it's also dependent on the type of data you have. So yeah, but eventually, like I mentioned, we'll see there's a way to even combine all different models and get the best one that's working for you. Yeah, so that's basically it. So I think let's just go back to the coding and have a look at those three methods. For all the machine learning we'll do from now on, it will be very straightforward. It's more of understanding. You just understand the model and the syntax, and then now the next step is always tuning the hyperparameters. That's usually the biggest challenge. So yeah, so let's just change to this other one here. So any question?
If I can take you back a little bit on this one.
Yes.
For the X, we said drop kyphosis X.
Yes.
Axis is equals to 1.
Yes.
For the previous model regression, we had
Yes.
given all the fields.
All the columns, yes. So it's basically, you can do that, or you can use this one maybe sometimes, especially like when you have so many columns.
Yes.
Sometimes it's easier to just use drop, because you can imagine writing all the columns and there are 100 of them. They can be a lot. So this is just an alternative you can use.
So by this we mean we
Yes.
pick all the columns other than kyphosis.
Yes, pick all the columns. Actually, we can just let's just display it here and you'll see. So let's give it a random name and we display it. So you see here, and if you display, so this, let's just say head, right, head. So, and if we display the actual df dot head, df dot head. So that's basically what we've done. So we've just removed this. Yeah.
Thanks.
Yeah. So it's usually faster. I think last time we just wrote all the columns, but yeah, you don't necessarily have to do that. Okay. So next thing we will do is now we start analyzing all the different machine learning models.
Steve, and just an observation. So
yes.
It appears like with classification, you're dealing with cases where we have a yes and no, or
Yes.
1 or 0 situation, right?
Where you have?
Where we have a case of yes and no, maybe absent and present. Basically, where you have
maybe that's for decision trees, but you can actually have multiple, like you can have as many as 10 different classes, not necessarily 2. For logistic regression, probably you can have 2 classes, but now for classification, it can be even 20 or more different classes. not necessarily two classes. So yeah, it's just that maybe the examples we're using today are showing, but we can try. I will just have a look at the loan data set and we'll try see if we can, because you can actually do more than two classes. It's not fixed to two classes. Okay. So yeah, so we can go to next one is so sklearn metrics.
So which are we using now? The classification we're using now?
So now let's go to okay, we can go to k nearest neighbors. So yeah, k nearest neighbors. So that should be k nearest. So this, it's called k neighbors.
Is this the same as k-means?
K-means is different, and k-means is used when, especially, it's used with unsupervised learning. So it will be more of, and then for, I think it checks on the mean. It checks on the mean error between the different, but they're very much similar. Between the different classes, like it will just check the clusters that it's finding and check the mean of the errors and cluster them. If the mean is too big, then it's now going to, a point will be on a different class, but it will, I think there's usually some very, I'll share some more like a video that shows how it works within the different iterations. So every iteration it makes, it improves in how it was classifying. And the same thing is happening with this one. Okay. So we can just give it a name. Okay. So that. So actually, like, basically we are replicating what's happening here. So you could copy paste this, but be careful with everything. Okay. So only the libraries will be different and the model will be different. So, but everything else will be the same. So that, and then we're going to just use them on default mode. So that, and then, so there are two more places you need to change. So we change that so that you're using the same model. This one we got a 76. This one, let's see. Yeah. Syntax error, but yeah, so this one gets a 72. But remember also, we are not doing any hyperparameter tuning. So this is just straight out of the box, running the model straight out of the box and see what the results are. So yeah, depending on which tree you are on, you will get a better score. This one doesn't seem to be changing. 72. Has everyone got that?
I was still typing the command.
Okay. Okay, just check. Just check, please. Maybe also, let me just take a short break as everyone is typing in. Just check on that. And then maybe the other thing we can check on is, let's try, we just do it manually for now. Check on the hyperparameters for the KNN and see if you can get a better score out of this. Just check on the documentation. Okay, nearest neighbors. Basically sklan. On sklan and check these aspects, especially like this one. Maybe try change it and so. Oh, did you give it the number of neighbors? So like right now here, we haven't given it number of neighbors, so that's not exactly right. So the default number of neighbors is 5. This is, and we know our classes are 2. So probably that's the first thing we need to change. Because yeah, it should not be that. So if you want to add this within the model, just come back to that. Go to the classifier.
Question, Steve.
Yes.
It's running, but how do you tell from where it's picking the data frame from? There's no place we have defined. There's no place we have defined the data frame.
So you remember this here, the X and the Y, white X train and Y train. So we already defined it here, and this is where we were getting it from. So the reason we've not done that again is it's the same one we were using here, and we don't have to do it again because they're already in these variables, and it will just basically be the same. Yes, so we can just do it once and we don't have to do it again. So next, so we just come here. So the other thing is here on the syntax, just check all these hyperparameters. Make sure the nearest neighbors are 2. First, they should be 2.
These are the number of columns.
These were the nearest neighbors now is in Kyphosis, like we are trying to classify them into 2 different classes. So absent and present. So if we had maybe a third one, like we said, this can be several. So sometimes you can find data with up to even 10. Basically, it's dependent on the data, but these neighbors are not limited, so they can be many. So it's the same thing with k-means. Probably we can even try use k-means as well, because it should work here as well. But okay, we'll just we'll just add it later. So just do this and see, tune the parameters and we'll see what you get. So just take a short break.
Hello, Steve, did we lose you? Hello?
Yeah, said he'll take a break.
Oh, okay.
Someone has a question?
Oh, you are
yes.
there?
Yeah, I was also, but I'm not.
Okay.
Someone has a question? guys, I think guys have taken a break. By just maybe 5 minutes. We go back live in 5 minutes. Okay, so I think we can just come back at 11:20. Just a short break. Take a short break.
You're back. Hello?
Okay, everyone's back. Just say hi. Feedback. Just say hi. Moses. Okay, let's just give them a minute. So okay, it's 11:21. I hope everyone is back. So thumbs up, please, if you are back. Justin.
I'm here.
Okay. Mary.
Yeah, I'm back.
Okay. Mercy. Well, thank you. Moses. Steve. Sparky. Okay. Sparky. Steve.
I'm here.
I'm back.
Okay. Awesome. Okay, so then let's proceed. So and I hope they're all making sense. I'd encourage you to also go back and read a bit, maybe just to get a better understanding if you've not gotten maybe what's happening here yet. But basically, the whole point, or even maybe what sklearn has done, is it's made work so much easier for everyone. So understanding machine learning algorithm is just basically just calling or using the machine learning algorithm is basically calling this. In the past, you had now the guys who are pretty good in mathematics and statistics to now create these models, and you'd have code that was probably even probably more than 100 or more lines. So if you go back to if you go check on the libraries within your Python, these libraries are stored here. So sklearn has just made everything very easy and straightforward for you. So you know you can use the model very easily. Yeah, so but in real sense, all the math and the crazy statistics is there in the background and doing that. So if I think you did classes, creating a class or creating a function. So basically now what we just do is call this and we just give the class what it needs, and it does everything in the background and gives us the results. So that's what made even now the likes of Python and machine learning and what we're actually doing today very popular and easy to do. So yeah, so with that, k-nearest neighbors, there's a whole lot more math. That's why I'm saying just go have a look. It will make much more sense now that you've used them. So and have had a brief overview of how they work. So also on tuning, you'll tune them better if you know what now each component means or what's the significance of each. So let's add another one. Let's add the naive Bayes. Naive Bayes that uses now the probabilistic algorithm. So naive Bayes. So it just okay. So it's like I said, you can use the tabs key. Programming doesn't like spelling mistakes. So that, and then we'll call the model. So model, we can call it GMB. Then we'll call back the that, and maybe we don't specify any of the other parts. Then we can now just copy these other parts since they'll all be the same. And remember, we haven't changed the test size. We're just analyzing on the base or on we're analyzing on the same test data, same test data size, no hyperparameter tuning, and just to see how does each model perform. Okay, so we still got a 72. I'd run it previously and got it a 96. Okay, 72. So right now it looks like the decision tree is the one that has the best score, right? So we'd also looked at support vector machines. So skline. So the only thing with this one, it requires the data to be scaled. So we could there is a method we use called scaler. So it will just basically scale all the data down.
I got a 74. Sorry, 84.
Oh, yeah, because the naive Bayes, I expect it to be much better. So there is also what you will start finding is people have preferences. Like over time, you'll start having a preference. Like I always use random forest, and it always works for me. So it's like when you're analyzing your data, you'll start realizing their machine learning models, even without tuning, you'll already get a really good score. So yeah, maybe just read on them and you'll start realizing, or you'll have a preference as well.
For the precision, you're
yes,
saying 0.74, which amongst these in the confusion matrix. Which one are you reading?
Sorry?
I've got a 1 at the precision level.
Oh, okay.
I don't know whether
that's
correct.
Okay. Okay,
Pardon?
so yeah, I think let's just do that by going back to our presentation here. So if we go back to our presentation, what precision means is this. So it's probably maybe the other thing we can do, just display the confusion matrix there as well, so that you know the significance of the or what's actually happening. So there is true, positive, and so for you to get precision, I think this is like if you assume if you were to use the example of a bowman, or like someone aiming, like, or a gunman who is aiming at a bullseye. So precision is how accurately they are hitting the same spot. They might be actually wrong, but they might be hitting the same spot perfectly every time. That's maybe an easy way of thinking of it. And like maybe accuracy. Accuracy is getting now the actual correct answer. So probably precision, but now you can also use these other two curves here. You remember the ROC and AUC curve. So you can use this. The curve should be known this. So what's happening is you're getting a that was precision.
What maybe I can share this so that you may understand
Okay.
what I'm talking about.
Okay.
You can see my screen.
Yes, we can now.
I'm talking about this one.
This 1.0 absent. Okay.
Is everything okay?
Display the confusion matrix. We just check maybe from that.
I thought this is it.
Okay, these are calculations from the confusion matrix.
So which from all these values, the one you're talking about is which one?
Okay, just do this. Add a cell. Add a cell. And now we'll call the confusion matrix.
By doing what?
Just confusion, right? Confusion, and then underscore matrix. Like I think we had done one in the previous exercise.
Yes, I think I have one here.
Yes.
Okay. Sorry.
Oh yeah, we had even already called it. But just now write the function.
I do what?
Just write now the copy paste that, and then give it y-test and predictions.
Y-test. Oh.
Yes.
Here.
Yes. Y-test and predictions.
That way.
Yes, just run that. Yeah, so basically now what's happening is this is, you're getting 0. Just give me a minute, sorry. Okay, sorry about that. So basically, yeah. So this is the like, you remember the true positive, true negative, and so the thing that's happening is so you're getting no false positives. That's why your precision is 1.
Okay. So
Yeah,
the accuracy
so,
of the model is which figure?
So the accuracy is at the bottom, the third row there.
This one.
Okay, above there, just okay, above again, next one.
Oh,
yeah, 84. Yes. So now yours is, you're getting 84%. So that's why I think that's why now the Oh, it's actually, yeah, that's why you're getting such a score. So,
So
and
this
of
is,
which it's actually a good thing. So there are no false positives. So, but there's still a bit of false negatives. But yeah, what kind of size of data have you used? Because I think they look few. Just scroll up. Still 0.3. Okay. Okay. Maybe, okay, it's still okay. Right now we're just understanding what's happening with the models. So that's okay.
okay, that's fine, thanks.
Yes. We'll use a bigger data set so that now at least when you're using a bigger data set, you'll have maybe not so perfect results. So yeah. Okay. So next here is so we were still on what are they called? So this is where we were. So one standard scalar. So what I was mentioning was you can use a standard scalar for there are some models that prefer the data to be scaled. Everything will be scaled from between 0 and 1. So as you maybe as we get deeper, you're going to see those aspects. So let's just and then there's also something called pipeline. So pipeline as well, we'll use it when we are combining several machine learning models. So this is a library that you can use to combine several models together. So we just do this, make pipe, and then next thing is import. So there are several support vector machines. We can just try out a linear one for now, or let's see if we can be able to see all of them here. So yeah, these are the possible support vector machines. So though not it's a bit mixed up, but there are linear species. Yeah, there are quite a number of them. So, but we'll just use the linear one. Yeah, then all the other steps are the same as we've done. So we just call it model SVM. Then, but this time, since we're going to combine it with a scalar, so we first scale the data. We first scale it, and then we use now the we now add the model, and everything else like in the others is the same. So just remember to change the names everywhere. Any question? We're using default values, so sklearn processing. So these are so spelling mistake. Okay, just a minute. So okay. Okay, just give me a minute. Sort something here. Oh, sorry, I think my mic was off. Okay. Sorry. Okay, so like I was saying, so you get different scores on different models. So you can now use like this specific pipeline library is very good when you're now maybe trying to combine different machine learning models. So you can or even maybe for when you're combining steps. This one is the best one to combine steps, or especially like on pre-processing. So like you want to do several things to the data before you do the final machine learning. So maybe can you just try and have a look at whichever maybe you prefer, and tune it manually and see if you're getting a better score.
From industry standards,
Yes.
The Genie is also, I think we had a model where the evaluation the consultant used the Genie.
Yes.
I don't know how. How they compare the Genie and the confusion matrix.
Genie. And that's now like with random forest or with all the models.
Actually, it's a regression.
Yes.
It's a
Okay.
logistic regression.
Oh yeah. Okay. Yeah, because it's also here.
I
Probably okay.
think to test, he came and calculated the Gini
Yes.
just to confirm how accurate you are, and
Yes. Yes.
yes.
Okay. Maybe like I just say maybe based on what we were doing or what we had mentioned in the PPT, like this is where the actual work happens. So it's a lot of iterations before you actually finalize on a model. And it's also dependent so much on the type of data you're analyzing. What is a good score depending on the type of data you're using. So what are the consequences of not having a good accuracy? So all of those things, and there are so many parameters you need to check on to get like to choose and to select a value. So all of there are so many variables, and that's where most of the work is. So I'd maybe not say this is the best one, because maybe in a different scenario it's not the best. So it's more of iterations, and factoring in all of those other aspects.
So
Steve,
is
I
the
got an error.
calculation of the Gini part of what we are covering? I mean, in scope. Is it in scope?
No. Mine is okay, or we'll just do general tuning and try just to see how we can get better performance. But now those other aspects now dependent on where the models are being used. That's why I'm avoiding maybe to go to the finer details of that.
Okay.
Yeah. So maybe just pick one model and try tune, and then try change a few values, and then we'll now go into using grid search and the different methods of using hyperparameters, of tuning by hyperparameters. So we'll do one here and see if we can get a good result. Okay. So maybe just give you 5 minutes, and then we see if we can just post your
Question,
results. Yes.
Steve, I'm getting an error. It's saying fit missing one required position argument and y into parentheses.
Within this.
Yes, the SVM.
This example. So you given X train and Y train, because fit needs 2 data frames, two columns. So,
there's the X train, yeah. There's the X train and the Y train.
Yeah.
I have defined that.
Okay, just a minute. So you can just do one. So maybe we just do that. 5 minutes, try tune, and then post your results, and then we do a grid search or we just use several of the hyperparameter methods to tune?
Steve, mine is having an error. I put the Y train and the X train, but it's still giving me an error.
Okay, just share, please. Okay, my train. Oh, just above the first line. The first line, you've only called you've only written linear SVC. It should have brackets within. Add another one before the closing brackets.
Oh, so I put two like this.
Yes.
Oh, okay.
Yeah. So, but like I said, it always happens. Even for me, it still happens a lot.
Okay.
Yeah. And especially like I think you've seen a lot of programmers with a coffee mug next to them. Yeah. Sometimes you'll even look at a page for like 5 or 10 minutes and you don't understand what's happening. You're probably getting a bit exhausted and need just a refreshment, and yeah, things go back okay. So just 5 minutes and then we go to
By the tuning, you mean playing around with the size, the test size?
no. Now, right now, we just leave the test size. So just look at one, like for instance, like if it's nearest neighbors. So look at these aspects here. So for the nearest neighbors, ours is 2, so it should be 2. But for this, like for instance, weights, there is uniform, there is distance. So try maybe say weights and then equals to maybe distance. Check another one. Try the default is auto. Try use this instead, and just and there is also maybe leaf size. The default is 30, so maybe try use a different one. So has anyone been able to make one perform better? So there is a so going back to this here. So there is this section here, and like I always mention, these were now like probably it will save you a lot of work instead of necessarily doing it manually, tuning every bit of it manually. So you could use these algorithms here. They basically just do iterations over and over again on and trying the results, checking the score. If it's not good, going back, and then so there's the first grid search we had gone through it. Grid search is kind of just pure brute force. It's just trying every possibility, trying every possible all possibilities that are there and seeing which is because you see eventually you'll find the one that has the best score. So that's what just grid search does. The next one is called random search. Random search basically it's a bit more smarter, or it just randomizes. So instead of doing one bit at a time, it will just now do it stepwise, do it randomly over all the different possibilities that are there. So it will try the different possibilities, and instead of going through each of the combinations that can be done, instead of going through each of the combination, it now will randomize, and hopefully from randomizing it's going to meet one that has the better score. Most of the time when you're randomizing, you will probably get the result faster than going through each bit one at a time. So yeah, it's more of like just think of like putting your hand like trying to pick the maybe if it's a can, if it's maybe a box that's filled with stones and sweets, picking one at a time, you'll make more mistakes than just doing it randomly. There's a higher probability you'll pick the sweet instead of the rock. So that's basically what the random search does. And all these others, there's a lot of theory in all of them, just doing a different approach. Bayesian is still back on the same concept we were looking at. It's now more probabilistic, so it will perform even better than these other two. And then some of these are used for gradient-based optimization. I think we'll look at it next time. It's usually so with the gradient descent, you'll see it being used a lot in neural networks, but there is a lot more. Like all these others here are very new, so we'll look at them randomly in the next classes. But maybe just let's try these two here, and so that you just get an understanding of how they work. Okay. Yeah, so let me just switch to so with the So I think I'd used the grid search on the previous exercise. So with grid search, this is the syntax. And basically you give it the estimator you're trying to use, and then the param grid. And basically the param grid is dependent on the estimator you're using. So yeah, if you come down here, you'll see maybe just can just get the library. So any preferences, which model do we pick? Which model do we pick? Anyone with a preference for any? We can pick this, but first maybe we need to know the kind of hyperparameters it needs. Okay. So for the Gaussian, so these are its hyperparameters. Luckily, they're not very many. Maybe it's not the best class, not the best example. Let's go for one with very many. So this is it here. So these are the different combinations you could use for this. So let's say so what having that these are the different combinations you can use. You can try with all of them, or maybe we can just try a few. So first thing, we have to create the param grid, which is tuple. Just give this. So we'll create a variable that holds the different parameters that are possible. So like this here, ours we're not changing this, so this remains default. And then for the weights, for the weights, these are the other possible scenarios. We could use uniform distance. So let's go for that. Anyone with a question or a comment, please? You're very quiet. Seems to be an error there. Oh, okay. Then maybe let's try something else like the leaf sizes. So this one is just a number. Wait, let's just try it at that, and then yeah. So after that, like we said in the previous section, once you call this, so you'll just give it the, so for this, like you've seen here, the syntax is you give it the estimator, and then you now give it the param grid, and you could specify these other aspects as well, but you just give this first. So yeah. What else? And then just run it, and then we'll just do everything else like we had done. So what you'll notice with this one is when you run the fit, it now doesn't work just immediately like before. It will take some time to run, but let's just check what's wrong. Valid parameter. Oh, okay, there is an issue with the number of leaf sizes. Something wrong. I think it's also, we had already specified this here. Okay. Are you still there, guys? Very quiet. Not sure if you're there. Steve, Purity, Moses, Mercy, Justin. No, I'm not sure if maybe my internet dropped.
No, you are audible. We can hear you.
Okay, you're just too quiet, guys. So
I
with
think
online,
energy levels zimeenda chini kabisa.
yeah. It's I think especially like with these MLs, it's they are usually a bit draining. So yeah, that's why like I was mentioning previously. That's why you see progressively, like when you're starting the class, at a syntax error hazikuagi. Everything works perfectly, and slowly you start seeing a lot of mistakes, and like things are just not working. But I think we've gotten the message through on what we were doing with classification. The only other things are on the other things are on hyperparameter tuning, which I think I'll just share this example here. Probably maybe guys are a bit tired, so I'll just share this example, and maybe one that I'll do on one of these models, so that then we try. This one will be a bit we can try maybe on a different data set and see which is the best model. We had two different data sets, so we can try the one for the loans.
When I run mine,
Yes.
it tells me that the grid search CV is not defined.
Oh, okay. Okay, but so there's this other data set here for the loans. The one for the loans, this is quite let's try. We'll try this. This has a lot more. What do I call it? Like a lot more columns, and then we can try use. There are different things we can use them as targets. So this not fully paid, this is probably like the guys in banking, this might be something maybe what you're interested in such a data set. So anyone who is not paying, then we need to know who is, we just try and classify all this data and be able to, like, given someone who comes and says the purpose of the loan they want is debt consolidation or what this, once you pick all these aspects, then I should be able to immediately predict whether this person will pay or not pay. So we can try. I think for this week, this will be the exercise we'll do. And so within just check this loan data set. So the column will drop when you are splitting, will be not fully paid, and will train with all the others. So yeah, I think let's try. We do this, and then since guys are a bit exhausted, we close it at that unless there's a question. Steve, I know there's something we also was waiting for. So there's something we call feature importance. Every single model has something we call feature importance. So if you come to, for instance, like this one here, you can create a data frame. So, just press tabs on. Okay. So for instance, like this. So like this, for this example, it will be really good. The one for the loan data set, it will be good because now we'll try analyze or we'll try maybe there'll be a lot of columns to check on, and maybe we need to know which is the most significant column. So we'll try narrow down on that with this feature importance. So the syntax is this. I'll share maybe just a script on how to go about this. So okay, thing is, so this should be the syntax or all of the models you'll work with. You'll see they have this. Just let's check XKeLearn. So just check on documentation, you'll see this feature important. So you just combine, once you've already fitted, then you just create like a data frame that has this will create like a call it will take all the columns and specify the importance of each. So from that you can draw a bar graph and you'll be able to maybe specify what is you'll be able to specify you'll be able to know which column has the most significance to the final output. But let me just share this because yeah, seem all a bit exhausted. So unless there is no other question, we close it at that. But this is the exercise for this week. Learn data set. We get everyone to get the best learning model and post your scores every day.
So the variables here will use both the categorical one and the continuous one.
Yes. So okay. So you'll find maybe depending on the model you're using, you'll find there are some that don't work well with categorical data, while there are others that work. So depending on the model you're using, you'll drop some and you'll use some. So, but yeah, just try. Let me not give any hints because you'll get a lot of faults as you work with them. So just check on this. First, do all the data exploration so that you understand what's happening in each one of them. And then once you do that, then now going to learn machine learning. That's okay.
That's fine.
Unless there is any other question, I think we can close
The
it
loan
at that.
the loan data is on the
Yes,
drive.
it's on the folder. Yeah, it's on the drive.
Okay.
And it's open. So just check there, download it, and then yeah. And you know, I think we also take advantage of the long weekend. The next class will be really hot, so make sure you are ready for it. So make sure you understand well these algorithms, because the next class is combining. It will be a lot of chaos, and we have to have a good understanding of all of this. Okay. Then I think with that, unless there's any other question, please, we can end that today. But you can always, if you have a personal question, you can always pose it directly to me. Okay.
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 Thank you.
Okay, welcome. So then I think close it at that. I'll see you next weekend.
You have a nice weekend.
Okay, nice weekend.